any questions on the homework? So we've had 3 assignments so far, 7-1, 7-3-1, and 7-3-2. 7-1 was our inverse and direct variation. 7-3-1 was our simplifying and multiplying rational expression. And 7-3-2 was our dividing. So far we've gone over multiplication and division. And now we're going to start addition and subtraction, being able to add or subtract 2 rational expressions. Now, whenever we add or subtract fractions, these rational expressions, the denominators have to be the same. They have to be the exact same for us to be able to add or subtract rational expressions, to add or subtract fractions. And whenever we get the denominators to be the same, we add or subtract the numerators. So if the denominators are the same, we can add and subtract the numerators. So if we look at this first example here, we have 7 over 4x plus 3 over 4x. Now, since the denominators are the same, we can add or subtract. Here, we can add the numerators. And the denominator is just going to be 4x. So we can add the numerators together. So we're adding, what? 7 plus 3. All right, guys. Since both the denominators were 4x, we can add the numerators together. So 7 plus 3 is 10. So we have 10 over 4x. Now, before we can say this is done, we need to make sure there are no common factors on top and bottom. If there are, we have to simplify them out. 2. So there's a common factor of 2 between 10 and 4x. And if we simplify the 2 out, the 10 goes to 5 and the 4x goes to 2x. So really, when we factor the 2 out, we're really just saying that this is the same as 2 over 2 times 5 over 2x, because we pulled the 2 out. And 2 divided by 2 is 1. So we're just saying that we have really 1 times our 5 over 2x, which is just 5 over 2x. Questions on this here? So we're simplifying here because there's a common factor of 2. So really what we're doing is saying that we're multiplying. So we can say that 10 over 4x is the same as 2 over 2 times 5 over 2x. Yeah. No, I was just writing out exactly what the simplifying step was. Because we really don't do this step here. We more do it in our head at this point. 2 over 2 is 1, or simplifying that 2 out. So it leaves us with 5 over 2x. If we did talk about the restrictions, I'm not going to ask you to list the restrictions when we're doing the addition or subtraction, is whatever is going to make the denominator be 0 before we start simplifying. So it's whatever value of x is going to make 4 times x be 0, which is just going to be x cannot be 0. Questions on how we added these two together? Let's look at B. We have 2x over x plus 6 minus 5 over x plus 6. Here the denominators are the same. So we can subtract the numerators. We can subtract 5 from 2x. So we can do 2x minus 5. Are 2x and 5 like terms? Guys, focus up here. No. Is there anything in common with 2x and 5? No. Since there's also nothing in common on top and bottom, 2x minus 5 over x plus 6 is as simplified as it gets. We can't do anything with it. And again, our restrictions, whatever is going to make the denominator be 0. Yes, and to find that we could set x plus 6 equal to 0. we would subtract 6 from both sides, telling us that if x is equal to negative 6, the denominator would be 0, so x cannot be negative 6. Questions on our addition or subtraction so far? Let's look at some more of these here. Our next one we have is 8 over 12x minus 5 over 12x. Since here the denominators are the same, we can subtract the numerators. And yes, 8 minus 5 would be 3. 3 over 12x. Yeah, there is a common factor of 3 on top and bottom with our 3 and 12. And if we reduce or factor out the 3 from 3 on top, it would be 1 over 4, yes, and x. So 1 over 4x. And if we were to list the restriction, it would just be x can't be 0. The only thing that's going to make that denominator be 0. Questions on that there before we look at the next one? 2 over 3x squared plus 1 over 3x squared. Well, our 2 plus 1, we can add them because the denominators are the same, which would give us 3 over 3x squared. 1 over 1x squared or 1 over x squared, because the 3 over 3 does simplify. And since the numerator, again, like the last one, simplified out completely, we write it as 1. Now, if the denominator simplifies completely, we don't have to write a denominator of 1. We only have to do that with the numerator. Questions on any of this here? Because adding and subtracting these rational expressions with the denominator being the same is quite nice. We ready for the next two? 4x over x minus 2 minus x over x minus 2. Since the denominators are the same, we can subtract the numerators. Now, we don't necessarily have to put parentheses around each one because it's a single term. We do have to be careful, especially if the one being subtracted has more than 1, because that sign is going to have to be distributed through. But here, 4x minus x is 3x over x minus 2. 3x is as simplified as it gets. X minus 2 is as simplified as it gets, because again, we're looking to see if anything's going to reduce. And it can. And it might be tempting to try to simplify or reduce the x with 3x and the x on bottom, but because of that subtraction, the x minus 2, it's stuck as a single term. We can't just simplify out if there's a plus or minus between it. Now, if they're being multiplied, yes, we can simplify. So this here, 3x over x minus 2 is as simplified as it gets. And our restriction for this one here is that x cannot be 2. Because 2 minus 2 would give us 0, so we cannot have an x value of 2. Questions on these so far? Let's look at number 4. The denominators are both x squared plus 1. So that means we can add their numerators together. So we're going to be adding 2x squared and 2. Yes, now we can't actually add 2x squared and 2 into one term because they're not like terms. Because when we add them, we'll just get 2x squared plus 2. But there is a greatest common factor of 2. And we need to factor and simplify as much as possible in order to determine if there is any common factor on top and bottom. And yes, x squared on top and bottom, x squared plus 1 on top and bottom is the same, yes? So since it's the same on top and bottom, it means the x squared plus 1 and the x squared plus 1 will simplify, leaving us with 2. So 2 over x or 2x squared over x squared plus 1 plus 2 over x squared plus 1 will add together to give us 2. So the question is how we got this one here. So when we look at this here, 2x squared and 2, is there a greatest common factor between the two terms? Yes, so we have that 2. And we factor the 2 out of 2x squared, we're left with x squared. Then we factor the 2 out of 2, 2 divided by 2 gives us 1. Because whenever it factors out completely, it's going to reduce to 1. Does that make sense? So we get this here. Restrictions. Now this one I do find interesting. There is a note. Because here we're trying to make sure that the denominator does not or cannot be 0. So here we're talking about x squared plus 1 cannot be 0. So we would subtract 1 to solve this here, telling us that x squared is equal to negative 1. At this point here, we would take the square root of both sides. Square root of x squared is x equals plus or minus, because whenever we take the square root of both sides, we put the plus or minus. Now the square root of negative 1 is I. It's our I term. And the reason that this is interesting is, well, the square root of negative 1 is I. So we're saying that x cannot be positive or negative I. I is an imaginary number. So this doesn't work. All this tells us is that there is no restriction. And if we graph this, x squared plus 1, we can see here that it doesn't cross the x-axis. There is not a value of x that will make this equation be 0. There's no real value, so there are no restrictions for this one here, because there is no value of x that would make it be 0. There's only imaginary values. Questions on this so far? So most of the time we will have restrictions with these rational expressions, but not always. Questions on any of what we've done so far with this addition, subtraction, adding or subtracting rational expressions with like denominators? Now for the rest of this part of the lesson, we're adding or subtracting with unlike denominators, because the denominators aren't always going to be the same. Fortunately, they might be, and most of the time are different. And if we have two unlike denominators, they're not the same, we have to find the least common denominator. We need to find what the first number or term is that will make them be the same. Because if we were looking just purely at numbers, if we said that we wanted to add 1/2 and 1/5 together, we can't just straight add. We can't just say 1 plus 1 on top and 2 plus 5 on bottom, because that's not going to be the same. Because what we have to do is find the first number that's going to make 2 and 5 be the same. We need to make them proportional, the same or like fractions. And yes, first number that 2 and 5 are the same as 10. Now we can do this by skip counting, finding all of our multiples of 2, and do the same thing with 5, 10, 15, 20. And the first number, the least common multiple between 2 and 5 is 10. So we need to make the denominator be 10. Well, 2 times 5 is 10, 5 times 2 is 10, so we're going to multiply our 1/2 by 5 over 5, our 1/5 by 2 over 2. And what that'll give us is on the left-hand side, 5 times 2 is 10. 2 times 5 is 10, so the denominators are both 10. On top, our 5 times 1 is 5. Our 2 times 1 is 2. So now we can actually add the two together and see that 1/2 plus 1/5 is indeed 7/10. Because we have to make the denominators be the same for us to be able to add or subtract. And the key to being able to do this is finding this least common denominator, this term that's going to make them be the same. So before we get into adding or subtracting, we need to find the least common denominator, or in just numbers terms, least common multiple. The first number that we can have, in this case, 8, 14, and 16 be the same. We're looking for the first number that all three are the same. Now, there's different ways to do this. There's two main ones. The first is referred to as skip counting. So what we do is take, say, 8 and find all the multiples of 8. So 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96. So we went out decently far, and we'll see if that matches up, because then we can do the same thing with 14, 14, 28, 42, 56, 70, 84, 98, well, 112, 126, 140. I went a little farther out because even if we look at 8 and 14, there's nothing in common. Okay, so that means I'm going to have to come back to 18, 104, 112. Okay. So 112 is the first number that 8 and 14 have in common. Let's check with 16. We'd have 16, 32. Well, 32 is shared with 8 and 16, but since it's not shared with 14, it's not our least common multiple. We have to keep going. Mm-hmm. 48, yes, it will get us to 112. 64, 26. So the least common multiple for 8, 14, and 16 is 112. Now for 8, to get there, and to make them be the same, we're going to have to multiply 8 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. For 14, 1, 2, 3, 4, 5, 6, 7, 8. And for 16, 1, 2, 3, 4, 5, 6, 7. Because again, we're trying to find out what's going to make them be the same. So with 8, we're going to have to multiply it by 14. 14, we're going to have to multiply it by 8. And 16, we're going to have to multiply it by 7 to get this least common multiple. Now for some numbers, this isn't bad. For others, it becomes a little more challenging because, again, here, 112. If we start getting numbers where the least common multiple is bigger than that, we have to go very far out before we start seeing that. There is another way to do this. And that involves our prime factorization. Prime factors of each of these here. So if we look at 8, our prime factors, we're going to factor through this. What is the smallest prime number that goes into 8? Well, 1, but 1 doesn't help us. So the next one would be 2. So is 2 a factor of 8? Yes. 2 times what? 4. Because 2 times 4 is 8. 2 is prime, 4 is not. What number goes into 4 still? Well, 2. We always start with the lowest one. 2. If 2 doesn't work, we can go to 3. If 3 doesn't work, 5. 7. And what times 2 is 4? 2. So now we have all the prime factorization. We have the prime factorization of 8, which is 2 times 2 times 2, or 2 to the third power. Questions on this so far? Let's do the same thing with 14. Well, 14 would be what? 2 times 7. 2 is a prime number. 7 is prime. That's the prime factorization, 2 times 7. And the last one, 16. Well, we can say 2 times 8. Well, 8 is 2 times 4. 4 is 2 times 2. Well, really, once we got 8, 2 times 8, we knew 8. We already got it. So we can say that this is 2 times 2 times 2 times 2, or 2 to the fourth power. Questions on how we found this here? Now with this method, once we get the prime factorization, the prime numbers that multiply together to give us 8, 14, and 16, we're going to look at all three of these sets of prime factorizations and take the most of each of these factors that they have. So if we look at 8, 8 has how many 3s? Or sorry, how many 2s? It has 3 2s, yes? How many 2s does 14 have? 1. And how many 2s does 16 have? 4. So we take however many factors of 2, or the most factors of 2 that each of these has. And how many is the most? 4, yes? 2 to the 4th. So part of this least common multiple, I'm going to take whichever one has the most. Since there's 4 2s and 16, I'm going to take 4. We're not concerned with the 1 or the 3 because 4 is bigger. Because the first one has 3 2s. Well, how many do I have listed here? 4. Do I have a 3 listed? Yeah. I actually have 4. The middle one has 1. I've got that covered. I've got 4 of them. We're not going to add them up. We're just seeing which one has the most 2s. That's what I'm going to take as part of my least common multiple. Does that make sense? Okay. Is there any other numbers listed in these prime factorizations? Well, yeah. What is it? 7, yes? The middle one has how many 7s? 1. How many 7s does 8 have? 0. 16 has 0. So how many 7s do I need? I need just one of them, yes? Okay, let's see what we have here. 2 to the 4th times 7. Now we could do that by hand. Or I can tell the calculator, tell me what 2 to the 4th times 7 is. 112. It's the same thing we found, yes? Because this least common multiple, least common denominator, is going to be the first number that all three line up with. Is going to make them be the same. Okay? Now I'm going to drive that again. It's at this point, we feel like we get it, but I want to make sure. I know I'm driving this point home. I'm being a little redundant here. But I want this to make sense. Because we said that the least common multiple is 112. And we already said to get 8 to be 112, we have to multiply it by what? 14, yes? Okay. Now here, we said the prime factorization was 2 to the 3rd. The least common multiple is 2 to the 4th times 7. This one here has 3 2s, and we said we need 4. So it's missing a 2, yes? And it's also missing a 7. Well, what is 2 times 7? That's fine. The middle one does have our 7, and it does have 1 2. But it's missing 3 2's for the least common multiple, because it has to be 4 of them and a 7. Well, what is 2 to the third? 8, because we said again on the last one we need to multiply 8 and 14 to get to that least common multiple. And if we look at the last one, it does have the 2 to the fourth. It's missing the 7. As we said previously, 16 times 7 gives us that least common multiple. So doing this gets us to the most efficient one, where we're not having repeats or multiples of these common factors. Does that make sense? Now, for this here, when y'all covered it, especially in Algebra 1, 8th grade math, there's different tricks and methods to doing this. One, I think that they talk about at the middle school is the butterfly method, where we multiply the we cross it and add kind of way, and that works, but it doesn't give us this least common multiple. And for most of what you covered in 8th grade math and Algebra 1, this worked fine, because the common or our repeated numbers were that in and of itself, numbers, and that the calculator could do it. We can simplify it nicely. It's not going to be as effective here, because some of our repeated terms are not going to be just numbers. They're going to be these expressions, which is okay. That's fine. But it's going to make it harder for us to simplify, because instead of having a quadratic on top, our x squared plus 2x plus 4, we now have a cubic. X cubed plus 2x squared plus 6x plus 4x plus 1. We now have something bigger to try to deal with. So it's going to be helpful to find this least common multiple. So looking at 9, 12, and 15, do we want to skip count the first way or the prime factorization? Yeah, we can do that first. We can do both of them. Because if we look at 9, the multiples of 9 are 9, 18, and 36. $99, 108. We'll stop there. 12. Let's see. 12. All right. 15. 30. Yeah, 75, 90, 105. Yes, 36 does match up 9 and 12 up with 12 and 15, but it doesn't match up with 9. 108, and then 120, 135, 50. So here we have 108, 120, 132, 144, 156, 108, 117, 135, 144. So it's going to take a while to get there. Huh? I think how far out. Yep. 144, 153, 162, 171, and then 180. 156, 168, 180, 165. So here the least common multiple is 180. It took us a while to get there, but we did get there eventually, especially 9. 9 took quite a while to make it all the way out there. So 180 is the smallest number that we can turn 9, 12, and 15 into. Now I also want to look at this as prime factorizations. So we're going to look and simplify these as prime numbers and multiply together to give us these 3. Well, 3 times 3. And since 3 and 3 are both prime, our prime factorization of 9 is just 3 squared. 12. Well, 2 goes into 12, and it's 2 times 6. 6 is 2 times 3. So the prime factorization of 12 is 2 squared times 3, because 2 times 2 is 4, times 3 is 12. 15. Well, 2 doesn't go into 15, but 3 does. 3 is prime, 5 is prime, so that is its prime factorization. Questions on this here. So our least common multiple, if we look at the factor, so if we look at 2, well, 2 only showed up in one of them, and it showed up how many times? Twice. So that means we'll need that factor of 2 twice. Now, if we look at 3, 3 showed up in 12 once, showed up in 15 once, and showed up in 9 twice. So how many 3s do we need? Because again, we're pulling it from which one had it the most. So 9 had it 2, 12 had it once, and 15 had it once. So one of them had 2 of them, one of them had 1, the other had 1. So how many do we need? 2, because we're only taking however much each one had. Since the 9 had 2 factors of 3, it had it twice, means we're going to take those 2. Because even though it does show up once in the other 2, we want whichever one had the most 3s. Since 9 had 2 of them, it has the most. We're going to take 2 of them. And lastly, the only other factor that we have is 5. 15 has it once, 12 and 9 do not have it at all. So we need it once. Questions on how we got the 2 squared times 3 squared times 5? Does this make sense how we got here? Because whenever we look at the factors, this prime factorizations, we want to see how many of each of these factors shows up. And whichever one has the most, we're going to take it from it. We're not concerned about the others, so since 2 shows up twice in one of them, we take 2 of them. Now 3 shows up in all 3 of these, but since 9 has 2 of them, we're just taking 2. We're not so concerned that the other ones have 1. Because again, we're trying to get them to be the same. And since 15 has 1 5, we just need 1 5. 2 squared times 3 squared times 5 is 180. So it is telling us the least common multiple is 180, and it is helping us figure out what we need to multiply these together to be the same. Now, since this middle one had 2 2s, and the others don't, well, I'm going to have to multiply all of them by 2 squared, so that they're all the same. Now, the first 9 has 2 3s, which is fine. The middle one has how many 3s? 1. So to get it and 9 to be the same, we need 2 factors of 3, yes? So we can multiply it by 3. So we get 2 3s. So they're all matching. They're all being the same. 15 does have 1, 3, but we need it to have how many? 2. Do we kind of see that? Because we're trying to get them to be the same. We're trying to find the first number where they are all the same. And the last thing that the other two are missing is 5. Is now they're the same. Because even though that they all do have a 3, I don't need to multiply it by more than 2. Because if one has 2, I just need to multiply the other 2 by 3 once. Now they all have 2 3s, 2 multiples of 3. Does that make sense? Kind of, sort of. And again, these here, there's not a lot to it, but it feels like there should be more. Because we're just trying to find the first number that they're all going to be the same. The first term that they're all going to be the same. So the least common multiple for this here is 180. Let's look at expressions. I find expressions to be a little bit nicer. Now, our two expressions are 6x squared minus 54. And our other one's 9x squared minus 54x plus 81. Before we do anything to, or trying to find this least common multiple, it's going to make them be the same. Factor it. Factor it first. If you haven't noticed the theme, I have them probably flipped. Yep, I'll need. Is it this one? No. Okay. So give me those one more time. 4x minus 16.
And 6x squared minus 24x plus 24.
Okay. Let's do this here. I had to redo the notes this morning and I missed this one. So if we look at this here, before we start finding the least common multiple, we need to factor it. We need to factor both of them. 4x squared minus 16. There is a greatest common factor of 4. And if we factor that 4 out of the 4x squared and 16, we get 4 times x squared minus 4. Now x squared minus 4 will still factor because it is a difference of perfect squares. Because our x squared would be x2 is, our 4 is 2 and 2, plus and minus. Because we want this in factored form, just like we did with our numbers. Now let's look at 6x squared minus 24x plus 24. Here there's a greatest common factor of 6. And if we factor the 6 out of 6x squared, we're left with x squared. If we factor the 6 out of 24x, we have 4x. And if we factor the 6 out of 24, we're left with 4. And now our x squared minus 4x plus 4 will factor. Since the third term is positive, the signs are the same and match the sign of the middle term. Negative and negative. The only factors of x squared are 4 is going to be 1 and 4 or 2 and 2. And for us here, this time we want the 2 and 2. And if we do check it, x times negative 2 would be negative 2x. Negative 2 times x is negative 2x, telling us that we do indeed have our negative 4x as our middle term. Okay. Here. So, we're going to need to see what the least common multiple is. The first thing we can make both of these be. So we could start with x minus 2. This expression has how many of them? 1, yes? The other one has how many of them? 2. Which one has more? The second one, yes? How many does it have? So for the least common multiple, I'm going to need 2. Because again, we're wanting them to be the same, yes? We're wanting them to be the same. We want them to be exactly the same. Since one of them has 2, the other is going to need to have 2. We can go up, we're not going to go down. Because I'm not going to remove one of the x minus 2's to get them to be the same. That's not going to help us. We need to go up to find the first number that they're going to match. We're not going to go down. The greatest common factor is the first number that's divisible by everything. That one's going to be smaller. Least common multiple is going to be either the same or a little bit bigger because we're going up. Since one of them had 2 factors or had x minus 2 show up twice, the first thing that's going to make them be the same should have it twice. Let's look at x plus 2. Here it has it once. The other one doesn't have it at all, so we need it at least once. This is why I like the expressions, because once we get them factored, we're just looking, okay, this has it twice, this has it once, so I need it twice. This one has it once, doesn't have it at all, so we need it once. We can visually look at it and see it. 6 and 4. So here we can do our skip counting: 4, 8, 12, 16, 20, 6, 6, 12. Hey, first number is questions on this here.